The final thing I want to talk about is how we harness value of interoperability and secure some interfaces. So I'm going to fly through this a little bit faster. Essentially, there are lots of interfaces emerging on the grid. We have to understand what we're going to do with them and how we want to secure it, right? So empowered consumers are at the heart of many ideas in the framework, and we spend considerable effort in the document exploring how the changing dynamic of interoperability empowers and empowered consumers will introduce new technologies, change operations, require access to and the development of new markets, and even affect resilience throughout the system. So let's take a look at a couple of case studies that really drive home some of these issues, right? So interoperability plays a very important but not yet fully understood role in system resilience. If we look at what happened to Florida during Hurricane Irma with the utility outages, we can look at how those outages progressed across the state. In truth, the data from that becomes a useful quasi-experimental situation where the hurricane affected operations across the state, and we could examine the different conditions on county and utility level service territories. And what we did is we looked at a whole lot of data, and we decided to characterize the impact that AMI penetration or that interoperability investments would have on the resilience of the grid. Now, we used AMI penetration as a proxy for this, and we plotted then outages in each county against the that they experience against the wind speed by when the outage happened, grouping the data here by those counties in blue, which have less than 50% AMI penetration, and those counties in orange, which have greater than 50% AMI penetration. We can see that with some confidence, there is a different outage performance. And when we go through the numbers and we create the statistical model, we found a few interesting things, right? So on average, a county should expect to have outages increase by 59% for each standard deviation increase in wind speed. But that number is attenuated by nearly 10% for counties with full AMI penetration versus those without any AMI penetration, right? This relationship has a nearly 99% statistical confidence. The only other statistically significant driver we found was household income, but that effect was only half as great as the AMI penetration. And so this study shows pointedly how a general investment in communications infrastructure and interoperability can be shown to improve the resilience of power systems, right? This is just a little bit of context now. And as we think about how interoperability alters the system, we wrestle with the fact that through interoperability, actions that are inherently local can have system-wide impacts and are often specifically intended to have a broader effect. So we have to think about the physical context for where actions are performed, how they are coordinated, what communications and interoperability are required, and how to cost-effectively unleash the potential of these devices. So we'll start with the physical function. What you're trying to do with a device or system is critical to understanding how we have to communicate about it. The interoperability profile would look different for a thermostat or an inverter or a microgrid controller, and it may even look different for a single device used in two different applications. And we then need to consider the communications protocol. Imagine the communications protocol as the envelope in your first-class mail. It gets your information where it needs to go. It has some constraints, like you can't ship a Harry Potter novel inside a letter envelope. But within that constraint, you can get information anywhere you want it to go. In fact, if we take this analogy a bit further, we can say the difference between the Postal Service and FedEx and UPS and DHL and the large object dedicated shipping companies that ship containers around the world is analogous to the different communications protocols. They each have different purposes, different latencies in their shipping speed, and different capacities in their envelopes or shipping containers. But the information or data model is different from the communications protocol, but equally important. The information model is what we use to convey the information inside the envelope. It is the language and the grammar and the syntax that allows us to meaningfully communicate with one another. From an interoperability perspective, specifying an envelope without content is just as worthless as specifying the content, but not the shipping mechanism. Because if you can't get the information to another device or system, the value of working together doesn't exist. But the ability to combine all of these standards relating to the physical function, communications protocol, and information model in many different ways leads to a combinatorially complex space, which we show here, where each of these clouds represent one potential approach to interoperability. And I like to use this cartoon to drive home the basic context for different levels of interoperability. Plug and play with direct communication is inexpensive and timely to implement. Custom and one-off integrations are time-intensive endeavors and expensive, and constrain innovation and value creation. So how do we get to a plug-and-play interoperability environment? We believe that the availability of testing and certification programs are important to achieve plug-and-play interoperability. So maybe we can get there through standards. So we used IEEE 1547 as a case study in the framework. And if you read the standard, it even has an entire section dedicated to interoperability in section 10. The challenge is that section 10 of the standard identifies 3 different communications protocols that could be used and still conform to the standard. And it's silent on the information model that must be used. So each of these communication protocols does have associated with it an information model, and they can be interchanged and used with the different protocols. Importantly, there's a footnote in section 10 that says, by the way, we also really like IEC 61850 data model, which is different from the other 3 standards that they mention. So in the end, we wind up with a dozen different ways we could communicate about the functions of that one inverter, relying on at least 4 different standards, all of which would conform to IEEE 1547. So the question is this enough specificity to get the testing and certification that we need to know what's going on in our system and how it's going to perform? Well, we did a study on this. We evaluated 240 smart grid relevant standards. We evaluated, we determined 169 of them were related or relevant to interoperability. Only 21% have third-party testing and certification available. Of those, the vast majority are for communications protocols. So if we were to randomly combine a functional standard with a communication protocol standard with an information model standard, there's less than a 5% chance of having testing and certification programs available to cover these 3 aspects of our system for a single new interface. And if we go back to the 1547 example, these 12 different combinations have sort of paralyzed the testing and certification community. While there are certification programs for the physical functions of an IEEE 1547 inverter, there are not any programs to certify interoperability conformance for the standard. If we compare that to California Rule 21, which specified the required inverter functions using Smart Energy Profile 2.0 as the communications protocol and IEC 61850 data model, the result is that a testing and certification program was developed under UL 1741 SA. So in the framework, we describe the importance of developing interoperability profiles that derive requirements from existing standards, but combine and apply these requirements with a specificity that can provide clarity to industry, stimulate innovation, and hopefully facilitate the introduction of testing and certification programs. So now we understand a bit about the new types of interfaces that are coming on, but the question is, what are we going to do about it? How are we going to secure it? So let's start with the NIST Guide to Smart Grid Cybersecurity, NIST or 7628. This was published several years ago. NIST and our industry collaborators took the conceptual model from earlier frameworks and thought about which actors in the system would benefit from secure interoperable communications. In fact, they identified about 50 different actors on the system, grouping them by NIST conceptual model domain. And while this helps you see who has a role in making the electrical grid work, this doesn't help us understand who they communicate with and how. So the authors put their heads together and tried to figure out who would need to communicate together and why, and came up with this. It is affectionately or derisively known as the spaghetti diagram, whichever perspective you're taking on this. So NIST and our industry colleagues looked at all of those interfaces and came up with yet another really boring table, but it's actually super helpful, because the important thing here is that each of the communications or logical interfaces shown in the 7628 spaghetti diagram could be grouped by their fundamental characteristics. And in the end, the 2014 guidance indicated there were 22 different categories of logical interfaces, and protection schemes and best practices could be somewhat normalized for interfaces within each category. So what do we do with these new interfaces? How do we protect them? Where do we even start? If we imagine cybersecurity of the grid as a constantly evolving puzzle, it might seem that these new interfaces are like brand new puzzle pieces that don't necessarily fit within the existing space. But maybe that's not the case. 7628 did a great job of examining the system interfaces across the grid, but as we have discussed, new architectures bring in new interfaces, as evidenced by these red arrows here, where we examine what new interfaces might exist between the existing actors in 7628. But the important thing here is that when we look at these new interfaces and we map them to those 22 logical interface categories, from the 2014 guidance, we realize that all of these new interfaces share meaningful characteristics with those original categories. And what that means is that we can probably learn from and build from the cybersecurity protection schemes and requirements for those existing interfaces. And we don't always have to start from new and throw everything out to start over. So in this fashion, we put together a fancy table. It's in the back of the Framework V4. It includes the logical interface categories and our logic for why some of these new interfaces fall into the old buckets. And so, maybe we should think of these new interfaces as puzzle pieces about which we can gain a lot of insight by examining our existing protection schemes. And maybe we don't have to throw out the entire cybersecurity puzzle just to fit these new pieces in. Maybe there's ways to make it work much more easily. So there's a lot of work left to do on all the topics we've discussed today. NIST is continuing to publish studies and provide guidance on these issues as we learn more about them. I also want to point out to you a couple of additional activities that might be helpful as you navigate the grid implications of the concepts we've discussed today. The first are the catalog of standards and catalog of test programs that NIST funds through a cooperative agreement with the Smart Electric Power Alliance. These databases are openly accessible and rely on stakeholder input to stay current. Each of you can access them. You don't need to be a SEPA member. The second thing are the interoperability profiles that we're developing with industry. 2 working groups have been set up at SEPA to develop interoperability profiles for managed charging of EV fleets for grid services and also for DER integration with the grid. And there's a number of different standards that we're pulling from in order to really develop a set of actionable requirements. I hope you now understand just a little bit better the relationship between interoperability, resilience, value, and cybersecurity. There's a lot of information in the framework. I hope that the concepts and strategies we describe and tools we provide will be useful to the community for several years to come. This is the final section, so any more questions are welcome.
Hi, thanks, Avi. I am monitoring the questions right now. I'm not seeing any, but I'll pause for another moment if anyone has any questions to put into the Q&A or raise their hand. Well, Avi, I think this is a good sign. I think you answered all of their questions preemptively. So NARUC just wants to thank you again for being a great presenter. As always, it was very valuable information. Before we head into our break, I would be remiss if I didn't mention that your presentation today is going to be broken up into different sections as learning modules and available on our website. So everyone on the call will be able to revisit these sections. And I also want to mention and thank Avi for working with NARUC on a recent publication titled Understanding Cybersecurity for the Smart Grid, Questions for Utilities. That short, brief paper that Avi helped us with on the project scope and outline for is available right now on our NARUC's website. I'll post a link in the chat, and it kind of gives an overview of some of the same issues Avi just talked about: interoperability and risk management mechanisms and considerations specifically from the PUC's perspective. So thanks, Avi, for that as well. And now we're about 10 minutes behind. We will still give everyone a 10-minute break. So if you guys come back on at exactly 2:30, then we will have Andy Bachman from INL give his presentation on ransomware. So thank you, everyone, and we'll see you right back here at 2:30.